Hello everyone, today we are going to talk about the flux jumping. Today, we'll cover 3 key topics to explain the concepts in this lecture. First, we will discuss the concept of fluxoids, which is known as quantized magnetic vortices that occur in type II superconductors. Next, we will explain the phenomenon known as flux jumping. Finally, we will discuss simple solutions to address the issue of flux jumping. This page contains parameters commonly used in Chapter 5. Type II superconductors allow magnetic flux to penetrate internally, forming fluxoids. When current is applied to such superconductors, the Lorentz force acts on the normal electrons that make up the fluxoids. The motion of fluxoids induced by the Lorentz force generates an electric field, which in turn produces energy and causes a rise in temperature. In a homogeneous type II case, the previously mentioned fluxoid motion can cause heating within the superconductor, leading to an increase in temperature. This elevated temperature results in a decrease in the critical current density, which in turn allows more magnetic flux to penetrate the superconductor. To explain flux jumping, let's consider a simple model, the beam model. When the critical current density decreases, the area within the superconductor that carries current density increases. This expansion results in a wider application of the Lorentz force and subsequently leads to increased AC losses. This model illustrates how changes in critical current density can significantly impact the stability of a superconducting system. Flux jumping should not be simplistically understood as just a phenomenon where heat is generated and critical current decreases. When flux jumping occurs, it leads to a thermal instability that perpetuates a vicious cycle. This continuous sequence of events can trigger an avalanche effect. When a screening current is generated, it causes the temperature to rise. As the temperature increases, the critical current density decreases, as previously discussed. This reduction in critical current density leads to more flux motion, which in turn generates additional heat, further increasing the temperature. This avalanche effect refers to a rapid, uncontrolled increase in the movement of fluxoids, which exacerbates heating and further reduces the critical current density, leading to more severe consequences for the superconducting system. In the context of flux jumping, in the right-hand power density equation, the elements such as conduction, Joule heating, and cooling are neglected. By excluding these components, we simplify the equation to focus solely on the conductor's thermal power density and disturbance. This simplification allows us to calculate a critical size for the superconducting material. Furthermore, particularly with low-temperature superconductors, one effective strategy to avoid the problem of flux jumping is to construct the superconducting wire using a multi-filament design. This design approach involves combining several thin filaments of superconducting material instead of a single, thick wire. In summary, flux jumping refers to a cascade and catastrophic process where a superconductor eventually loses its superconducting properties. To counteract flux jumping, a technique involving the construction of superconducting wires from multiple thin filaments, rather than a single thick wire, has been developed. This approach is particularly prominent in low-temperature superconductors. Consequently, most low-temperature superconducting wires are now made using this multi-filament design.